which arise in the food sector and features strong collaborations with the industry and other groups. Current projects include partners in Argentina, Austria, Germany, Japan, and Sweden. So thank you very much, Ian, for being with us and give us the pleasure to have you on board. And without any further ado, I'll hand it over to you.
Well, thank you, Savio, and thank you for Maria for hosting, and thank you everybody for attending. I will now see if I can play my PowerPoint.
Yeah.
Okay, so welcome again, everybody, to this webinar. To build on what Savio had told you, I'm at the University of Cambridge in England, not the one in the US or the one in Canada or the one in New Zealand. Okay, and also I am not from Canada, the US or New Zealand. This is a Northern Irish accent. So apparently Savio wants you to hear people like me speak so you can learn about speaking in English. So this is actually an Irish accent. So you might find some of the words a bit strange because they're just spoken and presented differently. Anyway, so that aside, I'm going to talk to you about this whole concept of pastes and the idea of paste extrusion and paste forming. And the first question you're probably asking is, what on earth is a paste? So let's move on to my next slide here, if I can get it to move. Okay. Just trying to get my slides to move. Oh, there we go. So, like you, I'm a chemical engineer, and hopefully you're into the idea that chemical engineers like multi-phase flows. So what sort of multi-phase flows do chemical engineers often deal with? Well, they often deal with gas and liquid. And if you got your gas distributed in your liquid, you have a bubbly liquid. Or you have a cake batter, which is why I go to Argentina to work with people on cake. Okay, add a bit more. Oh, yeah, add a bit more gas. What do you get? Well, you get a foam. And if you have quite a bit of air or gas, you'll have a wet foam, even more gas, and you'll have a dry foam. Okay, so that's gas and liquid systems. Another one you'll obviously be familiar with, hopefully, is gas-solid systems. So when you don't have very many particles, you're talking about conveying, pneumatic conveying. Add more solids, you get into fluidization. And even more solids, you'll get into avalanches and things like that. Very dense particle motion. Another category, which chemical engineers work a lot in, is liquid-liquid dispersed systems. And of course, those are emulsions. So the last category to come along this is liquid solids, okay? And these are suspensions. So typically you're talking about particles, which of course we always describe as being round. But those of us who work with particles know that very rarely are they ever round. Okay, and they are dispersed in a continuous phase, which is often a liquid or something which we'll treat as a liquid. Add a bit more solid, you get a dense suspension. And these can become slurries, okay? And they're notoriously non-Newtonian. Add even more solids, and you get to the thing which we're going to call pastes. So pastes are highly dense suspensions. If you add even more solids, you end up with a soil. Okay, and to find out more about soil, you go and find a civil engineer and ask them about soil mechanics. So what we're doing is talking about something at the boundary of chemical engineering and civil engineering, which is very, very dense suspensions. Okay, and in the UK, these are often described as pastes. The reason why we're working on paste is because actually there are a lot of pastes around. So Savio has also noticed that I might talk about foods a lot. So here's an example of materials which are made by forming, okay? And these are examples of things from breakfast cereal to pasta, okay? At this point, I have to say that pasta is not a paste in the context that I would use. That's because pasta, based on durum wheat, is often viscoelastic. And the materials I'm going to talk about are not viscoelastic, they're viscoplastic. And unfortunately, in some languages, the word paste translates as pasta, which means you get confused. So I had an Italian PhD student a few years ago who could only really talk about his work in English, because as soon as he started talking in Italian, everybody got very confused. So that's the food bit out of the way. Other ones are in the manufacture of agrochemicals, okay, particularly for making dispersions for spreading on crops. We'll see a bit about they're actually used to manufacture machine tools. So here you can see these lumps of metal with holes in them. Those are used typically for drill bits and for metal machining. Another case is in terms of commodities, like Ariel is a detergent compound, very common here. I'm not sure if they sell it as Ariel in Brazil, but Procter & Gamble and Unilever and Henkel make a lot of their projects in the form of pastes. Then you can use them for even more interesting things like technical ceramics. And this is an example of a technical ceramic, which is used the insert for a gas turbine blade. So this is used to make the cavity that the cooling air goes around inside a single crystal gas turbine blade. And that also applies to aero engines as well. And the last category we've worked a lot with are pharmaceuticals, in forming pharmaceuticals to make pellets, etc. So what links all these categories together is that we have worked on examples of paste in each of these industries over the last 20 years or whatever. Okay, so there are a lot of pastes about. So that's why it's a good point to study them, because obviously people are interested in how they behave. So the key thing is pastes are examples of soft solids. They're somewhere between a stiff liquid and a soft solid. And this picture is an example of a bit of modeling clay, which was distributed in one of my lectures on the topic, and the students are given the lecture to make something useful out of it or something interesting, and there's a prize. And this is a prize winner a few years ago. Okay, so I have the title of being the professor of soft solids and surfaces. And so this is one of the reasons why I've got that title. Okay, so in terms of engineering pastes and using paste in engineering, there are two sort of scenarios we might be interested in. The first one I would call about when you want it to flow. And this is where you want your material, I'm going to use that laser pointer, your material to go through a duct or whatever. And the key thing you're interested in is what is the material going to do as it flows along that duct? How much pressure do you need to get it through there at a given flow rate, whatever? Okay. And here's an example of a paste flow. Chocolate, liquid chocolate, is actually a very dense suspension. Okay, it's not a very stiff paste, but it is in with the paste. And here we have a coating system, and you're interested in how it flows over that surface. Okay, now I'm not going to talk much about flow, because from my point of view, it's not that exciting. Okay, what I'm much more interested in is forming, where you take this ability of the material to hold its shape to create a product with a known shape, an extrudate. So your mechanical engineering colleagues will talk about net shape forming and things like this, and it's basically extrusion. If you know people who work in polymers, we use polymers because they keep their shape in these forming operations. Okay, and this is an example of an extrudate, which has got its own strength and hold its own shape, and actually you can make it into a helical coil. Okay, so by changing the shape of this die, the thing that we move, the paste through, we can control the shape of the product. Okay, and I think if you go back to that picture of pasta and the machine tools and the technical ceramics, okay, they're all generated by extrusion or net shape forming methods. So to do that, we have to understand how pastes behave, and particularly how they flow or move going through a forming operation. So I've got one equation which is talking about, one slide which is talking about equations, okay? So hopefully you might recognize these three equations as being the standard chemical engineering equations for flow. The top one is your continuity equation in 2D, and the second two are the Navier-Stokes equations to describe how the pressure and the velocity, V, are related to the size, the Z part, the body forces, the gravity, okay, the rate, the velocities, and then the ability of the material to actually flow. And that comes up with this thing, which is simply mu, the viscosity. And if you work in Newtonian systems, you stop there and off you go and you solve this partial differential equation or set of partial differential equations. If you work with paste, this is where it starts, because what we have to do is identify what the form of the rheology is and what is that constitutive equation. And there's a lot of work in Brazil on paste-related systems and soft solids to do with waxes and waxy crude oils. Okay, so if any of you have colleagues who are working in that area, this is where they'll get excited and start arguing about constitutive equations. Okay, so the first thing then is the rheology. The second thing which I've underlined here is what's going on at the wall. Okay, because normally with a Newtonian fluid, everybody knows what it does at the wall. It does nothing. Okay, you say the velocity is 0. Well, we're going to find out that pastes aren't Newtonian fluids, and they do strange things at the wall. And that's what makes it interesting. Okay, so we're going to find out a bit about the rheology. We're going to find out a bit about the wall, and then we're going to figure out how to put them together. So off we go. Okay, so the first thing to note when you're talking about rheology is, well, I've got at least 2 children. Actually, I have 3, but this picture was taken when there were only 2. But I was talking about soil mechanics and dense suspensions, put a bit of liquid in there, and hey presto, you turn sand into a modeling material. Okay, so these have sizable yield stresses. So what we're talking about is a rheology of material that has a yield stress. If you don't exceed that stress, it doesn't flow. If you do exceed that stress, the question is, how does it flow? So we have to try and figure out what is the rheology of these materials, not just in simple shear, which is what you have in pipe flow, but in extension. Because whenever we're changing the shape of something, we're usually putting it through a change in shape, which means we're extending it. And measuring these things is not straightforward if they have sizable yield stresses, which means you need big forces, or if you imagine it's something like this sandy material here, which means it's full of sharp particles, and if you want to put that in your rheometer, the person who owns the rheometer might ask you to sort of pay for the tools before you use it, because it will just scratch them and turn your nice smooth plates into nice rough plates. Okay, so there are some issues, and we'll talk about some of the issues in measuring them as we go further. Okay, so that's the rheology. What do we do for the rheology? Okay, the problem we have here, or the challenge we have here, is rheology is an assembly property. It's a property of the assembly, all the things together. But as you see in my little sketch there, pastes are actually heterogeneous at some length scale because they're particles in a binder. Okay, and as a result of that, this heterogeneity gives rise to features which have different timescales associated with them. Okay, so that means when we're talking about the rheology, we're somewhere between solid mechanics and fluid mechanics. So solid mechanics are characterized by the yield stress. And if you've got any rheology friends, they will tell you there's a big argument about whether or not there is such thing as a yield stress. And this is where the word rheology takes on quite a lot of similarity with the word of theology. Okay, there's a lot of belief and assertion going on. Anyway, moving on, we have the yield stress, and this is all to do with strain, the cumulative amount of strain going on. Whereas back to our fluid mechanics, which chemical engineers are quite happy working with, you're talking about viscosity functions and strain rates. So whenever the material is below its yield stress, everything is characterized by strain. And whenever things are beyond that, then it's strain rate. But then we have to add in the time domain. So in a fluid system where effectively you have molecules surrounded by other molecules, we're talking about very much micro scale, nanoscale effects to do with relaxation of molecules, potentially diffusion. Whenever we're talking about particles, and in paste, we're normally talking about much bigger than colloids, so somewhere between microns and millimeters, but obviously when you get to sand, you're much bigger than millimeters. Then you have macro effects related to the movement of one phase relative to the other, the liquid moving relative to the solids, or potentially breaking and thus aging. So we'll talk a bit about that towards the end of the presentation. So paste rheology is not straightforward. That's just the rheology. Then we get around to what's happening at the wall. Okay, and we have to know whether or not we have a smooth wall or a rough wall. So in this part here, you can see the streamlines are very different if we have a rough wall, because it will hold material back. If it's a smooth wall, it will all slide along the wall. And this is the strain rate. So you can see there's a large change of direction and thus strains there. So that's why we have had this arc of strain rates here. And along this part here, we have immobile material in contact with mobile material. So we have very high strains at that junction there. And in fact, that can cause rupture of the paste, particularly in the food system. So we need to know what's going on with the wall, because hopefully you can agree that those flow patterns are very different. And in forming, we will be changing the shape, and thus we will be doing things like this, making it move relative to the wall, and thus we need to have to know this in order to design a die properly, because the dies can be quite expensive to build, and you need to try and build them as efficiently as possible. Then the last thing we have to think about, how do you model this? And I've called them bifurcating materials, where some of the stuff doesn't move and some of the stuff does move. And if you are going to use a solid or soil mechanics mode, you have to identify that. And you do that by doing calculations which identify the regions of high strain rate. In fluid mechanics, the normal way to do this is to use a regularization method, which treats the material when it's below its yield stress as very, very viscous. Okay, so effectively it changes viscosity by orders of magnitude. And that's where you will hear the word regularization used in terms of solving the Navier-Stokes equations for pastes. But if it actually isn't moving, it's a bit of a cheat. And I'll talk about circumstances where we need to know whether it definitely is moving or not. However, being engineers, we use the one that's most appropriate for the system that we're working with. Because if we can get away with a simplified system, we get away with it. Okay? And it's then important to identify what the limitations on our estimates or our simplifications are. Okay, so the question I want to talk a bit about today is what goes on at the wall. The wall question, does it stick or does it slip? So because we have high stresses, shear stresses acting at the wall, often there's a rapid change in velocity near the wall. And it appears to change velocity over a very small distance, and we might call that slip. Okay, so here's a little schematic of what might be going on. So in standard pipe flow with no slip, the velocity at the wall is 0, so our velocity profile is something like this. And if you've met a Bingham fluid in your fluid mechanics notes or something like that, you've probably learned about this sort of profile, velocity profile. In a pipe flow with positive slip, there's actually a change of the velocity at the wall, and that will be related to the shear stress that's acting there. So it's as if it's sliding along the wall. Now, if we think about extruding, we actually want that to happen, because that means the amount of material that's sheared actually is limited to the region near the wall, and the rest of the stuff moves through with constant composition and everything like that. And this, because pastes do this, I'm letting you into the secret, pastes do this a lot. That's why people use them a lot, because you can extrude them into nice shapes quite reliably. But it does mean that if you're trying to model it, you have to know things about the slip functions. So, shall we show you how we know this happens? Okay, so being in Cambridge, we have access to this place here, and this is Professor Lynn Gladden's Magnetic Resonance Research Center. So this is basically a center where there are a lot of machines like this, which are MRI machines. Now, some of you might have experienced an MRI scan. Okay, as you can see, this is not the size of a medical MRI scanner. This is designed for scientific scanning, so effectively putting chemical engineering systems in there. And there's two reasons you can tell that this slide is quite old. First of all, it's telling you that this was done by Eloise in 2005, and that's Eloise back there. And the other reason you can tell it's a bit old, because look at the size of the screen, okay? Some of you might not recognize that. That's a VDU, okay? When I was a lad, okay? And that's the computer that's running the thing. Okay, so this is giving you an idea of the setup here. Now, what you can't see here is basically this is a big magnet. or rather, that's a big magnet inside a really big cooling system. Okay, and inside that is this RAM extruder, built to fit inside that camera, so we can take material and extrude it. Okay, and we extrude it, and we have the vision region just going around the die. So here, I'm going to show a video. This is an MRI image of stuff going through a square entry die. So this is the wall of the die going along there. Okay, so if this works, I have to try and figure out how to get this to work. We didn't try this. Okay, this is the typical. That's how I do it. Okay, right. So what you can see is those bits of black, white, and gray are changing. And that's related to the material inside there flowing. Now, you can't really tell a lot from this image because of the way that the data are collected. But the important thing is we're actually, for each of those pixels, we can work out the local velocity, which means we can actually map the velocities inside this system. Okay? The other thing you can see is that this stuff isn't the same color everywhere, and that's because this is a paste, and they're quite irregular systems. Okay? So there's a lot of noise in the data. Anyway, so we got the video to work, so I'm very happy. Right? So let's see what happens if we look at these velocities. Okay. So what we've got here is a schematic for cross sections in our cylindrical system. So we had a barrel feeding a die, and what we've got here is slices across the diameter. Okay, so we're looking at slices and looking at the velocity. And this does say biscuit dough. Okay, in Portuguese or Portuguese American, it's cookie dough. Okay, so this is literally making biscuits. So what we can see here is this is a velocity in the downward direction, z, divided by the RAM velocity. And up here, you can see that it's this value of 1. So that means that everything is moving at the RAM velocity, which means it's moving in plug flow. And the scale here is the radius divided by the radius of the barrel. So as you can see, apart from right up against the wall, everything is moving at the same speed, which means we've got almost total slip at the wall. If we go down to the one at the bottom here, this is in the die land, as we call the section that you're extruding it through. There's your velocity over the RAM velocity. It's much bigger than one because it's a narrower area. And you can see that this is all normalized against the die land radius. It's almost the same velocity. And then as we get towards this, you can see that it starts to accelerate as it gets towards the middle. And that's what you expect with a converging flow. So what do we see here? Well, we see that wall slip is a reality in these sort of systems. Okay, we can see that the velocity is quite complex, and we can see at this slice, this is really noisy, and that tells you something about, first of all, the pastes, okay, and secondly, how regular or how good these measurements were back in 2003, 2004. Now, MRI is really nice if your material is actually compatible with an MRI system. The one thing about MRI is you don't really want any metal anywhere near it. Okay, and for some of the systems I'll show you, they won't work in MRI systems. So it is this paste, these pastes do slip. Okay, so it's good for pumping and extrusion because it means everything moves through as a flow. So the limiting cases where your wall shear stress for your slip is less than yield stress material, and everything just moves. Once you get it to change shape, it flows through quite nicely. It's bad in these two circumstances. First of all, if it's happening in your rheometer and you don't know about it, because then you interpret your data as being the bulk properties of the material, where actually you're measuring the slip properties. So if you're working in rheology, you'll know this, that there are different ways that you have to check that you haven't got slip in your system. So you have to know how do you decouple your numbers from a rheometer if you might be getting slip. Okay, so how might we describe this? Well, if you're doing a fluid mechanics work, you might describe this in terms of the Navier slip, relationships, and this is the simplest relationship for slip behavior that you'll find in fluid mechanics. So your relationship with the wall shear stress and the slip velocity, and beta is the Navier slip coefficient. And it will go from infinity to 0. So we normally set that for infinity in our standard Newtonian flows because there's nothing moving at the wall. If you're talking about Coulombic friction, and hopefully you're familiar with something like this from physics days, you relate the wall shear stress to the normal stress acting against the wall, and then some cohesion sort of measure. And this is where we get into the particulate nature of paste, because if they're very dense, they will be exerting strong normal stresses on the wall, which gives rise to the local shear stress being related to the normal stress, and thus the slip velocity. So we have to know, are our slip behavior for our pastes related to the total pressure or the normal stress we're actually exerting on the wall? And if you have a fully rough wall, okay, then your wall shear stress is just related to the bulk modulus of the behavior, the bulk yield stress of the behavior, the material is just shearing internally. So this is the limit for a paste that would actually be, it would actually be shearing completely at the wall. So there's some really nice work that's been done over the last 10 years or so on tying these sort of things together. And this is called the mu-I rheology work by people like Jean Patel in France, for a theory of granular suspensions. And this is really nice if it works for your material. For our materials, it usually doesn't work because our materials don't usually involve round particles and they're really, really dense. But that's where we would start in terms of theoretical framework. So here's a story for you. We're interested in a paste that does things like this. Okay. Now this is made from tungsten carbide. Okay. And tungsten carbide is the second hardest material known to man, and it's used to make machine tools. And that's the material used to make these machine tools and drill bits, etc. And it's made in Austria and elsewhere by a company called TSED. So a lot of our work in this field for the last 10 years has been supported by TSED, because this is fundamental to the manufacture of a whole series of their materials. So tungsten carbide, W for tungsten, C for carbon, is a bit dense, and it won't fit in an MRI machine, okay? Because it just won't, okay? So we've had to come and look at other ways for doing this. And our question is pressure-dependent wall friction. Is it happening with these materials? So, okay, normally we'd say, how do we measure wall friction or wall slip? Well, the first one would be in a classic rotational rheometer. We'd use parallel plates, and we change the gap height, and there's some work done by Prudhomme and characters, and that allows you to decouple that. This material, tungsten carbide, it will basically erode your plates, okay? And it has a yield stress which is a lot higher than most rheometers will handle, so that's not really an option. Another one is to typically use ram extrusion or capillary rheometry, and you interpret the data in terms of Bagley plots. And I'll talk about Bagley plots in a moment. And then another method, which I'll talk to you about, is one we developed for these systems, which we call a two-stage Bagley plot. Okay, so, and here's one of the materials we used as a model material, which is simply soap granules, solid soap granules, which are actually quite soft. Whenever you compress them enough, they will flow together, okay? And the other good thing about solid soap is it's a very low paperwork material. You don't really have to worry about the health risks of soap granules. And it's very easy to clean. So that's another thing. So now what I'm going to do is introduce you to the Bagley approach and introduce this book. So Paste Flow and Extrusion by John Bembo and John Bridgewater. So John Bridgewater was the Shell Professor of Chemical Engineering in the department here when I joined. So he was my first boss, and he got me involved in pastes, okay? So what John Bembo and John Bridgewater did in looking at paste was say, well, let's take a very simple approach, treat it like a simple engineering plastic. So we'll extrude something by ram extrusion, and we'll measure the extrusion pressure Px from a barrel diameter of D0, a die line diameter of D, of length L at a given velocity, and we'll just relate the extrusion pressure to a term dominated by die entry, that's the extensional flow in the die entry, which was related to the change in area, so the log d naught over d, and then something to do with the paste yield strength. And that's what these terms here are. And then along the die, we say, well, we have a flow with a wall shear stress, and it's related to L over D. So what you do is you fix this bit by just keeping D naught over D constant, and you change L over D. And then you plot your extrusion pressure against L over D, and the gradient will give you the wall shear stress. And that is effectively a Bagley plot. You'll find it written slightly differently in the polymer literature, but that's what you do. You change the length of the die, and you find the change in pressure, and that gives you your wall shear stress. So it does require a few experiments, though. Okay, and this is the sort of result you get from these wax binder tungsten carbide pastes. So these are the stresses in orders of megapascals. Okay, just remember 1 megapascal is 10 bar. Okay, that is not a soft material. Okay, so the yield stress, the sigma y term, in terms of these velocities, is going from about 1/2 to well over 1 megapascal. So that means this stuff is pretty stiff. Okay, and your standard rheometers won't shift it. So that's another reason why we have to use ram extrusion to characterize it. The other plot we got here in the red is the die-land behavior. That gives us the wall shear stress. Okay, and we're talking about 0.1 to 0.4 megapascals. So that's quite a lot of work to make it move along a die-land. Okay, so this gives us a way of characterizing the materials. If we change the formulation, we can find out what these numbers are, and then we can then put these numbers into simulations, whether or not it's a solid mechanics or a soil mechanics sort of code, in order to model what we'll go and find out the pressures. So in order to find out if there's any pressure effect, we need to be a bit cleverer about that. And this is something that we did, and Matt Bryan did this, and then Harry Ayton worked on it more recently. I was saying, how do we measure wall shear stress while we want to control the total stress? And this is this thing called a TSED. So this is a secondary extrusion die. And this is what it looks like. So above this thing is a great big plate with a barrel, and that's that bit there. And that extrudes it into effectively a second barrel. So we extrude from this diameter into this diameter, and then we have another diameter at the bottom. We have a secondary die. So we might call this a primary die, and we might call this a secondary die. So we make the material flow from the top through one change in size and through a second change in size. And rather than measure the extrusion pressure, we measure the normal stress acting against the wall with pressure transducers, and that's what these things are here. These are pressure transducers, and we measure the pressure at the different points, because here we effectively have a pipe flow moving along that system, and by the gradient in the normal stress, we can work out the wall shear stress. So it's a relatively simple concept. It's just a bit complicated to make. Okay, and the other thing we can do is we can change the length of the secondary die. So if we make this shorter, it means we don't need such a big pressure drop in order to extrude it, which means the pressure in the primary die will be smaller. And if we want a big pressure, we make the secondary die longer. So that means we can work at the same velocities, okay, and we can manipulate the total pressure independently of that. The other advantage of this system is that by having this first die entry, we're also sharing the material, so it's actually in its flowing state, which is what we want to make the measurements on, rather than in the pre-compacted system in the barrel. And this is the very first TSED, which Matt built. And this led to a second one, which Harry built, which, like all second versions, benefit from being the second version. So the second version has 5 of the pressure transducers, and they're not all in a line. Okay, they're orientated around the system, so we're actually measuring measurements, we're making measurements which aren't affected by anything directly upstream. Anyway, so that's the system we built for doing this. And this is an example of what you might see in terms of the ram pressure, the pressure here. So that's the force divided by the cross-sectional area against the distance that the ram has traveled. So it pushes material down here and it flows along there. And this is the extrusion pressure that the ram is measuring. But of course, that has a bit to include the change in area as the material flows from the barrel into the primary die. And then we have the green, the red, and the blue. These are the local measurements of the normal stress. And as you can see, they lie in the right order. And what we can do is plot those against position, and then we will get an idea of what the wall shear stress is. So that's the concept. And here's some results for the measured pressure against the distance from the TSED chamber. Okay, so that distance is effectively the distance from up here. Okay, so the distance along the die. And you can see, oh, look, they look quite straight. So that's quite nice. And from the gradient, we get the wall shear stress. And then I need to point out that this is not for a tungsten carbide paste. This is for a microcrystalline cellulose-water paste. This is a pharmaceutical material. Now, the reason why you're not seeing a tungsten carbide paste results is because they're confidential to the company. Okay, so another reason why we do things with soap flakes is because we can publish those quite happily, and the microcrystalline cellulose work we can publish quite happily, but the company-specific material, obviously the company hold on to those. And what you can see here is plots of wall shear stress against the plate velocity, against different ways of measuring it. You can see we've got error bars, so there's some variation. What can you see here? You can see that this wall shear stress is strongly related to the velocity. So it goes up quite a lot with the velocity in a parallel way. But in terms of the different lengths of the die, because that's what the 35/3, 22/3, and 10/3 mean, you can see that this wall shear stress is not really related to the length of that secondary die, which means it's not pressure dependent. Okay, so for this pharmaceutical material, we don't have to worry about pressure effects. For the tungsten carbide ones, you can work out for yourself why they don't want me to show you the results. Anyway, so let's move on to something else. So what else might affect wall slip? Well, what happens if we change the wall material? Okay. Typically, you will do experiments in a lab with something like a nice bit of stainless steel. What happens if your machines are actually made from a different material, stainless steel or tungsten carbide or even polycarbonate? Because we're always talking about interactions between the material and the wall, so the nature of the wall will become important. So actually what we have is 3 sets of identical apparatus. This one is made out of polycarbonate, this one is made out of stainless steel, and this one is made out of tungsten carbide. Okay, so what we're going to do is show you the results for extrusion of a given material through these 3 things, identical tests, and what happens to the wall shear stress and slip behavior. And again, using this Bagley approach, this is for solid soap. Here's your wall shear stress. Here's your extrusion velocity, so the slip velocity for these materials. The blue one is for the polycarbonate. The orange ones are for the stainless steel, and the black ones are for the tungsten carbide kit. And the line is from an approximation used elsewhere. But hopefully what you can see is there's definitely an effect of the interaction of the solids, in this case the soap, with the wall. Okay, the reason for that we could cover in questions if you want, but there are a whole series of things related to the chemistry of what's going on the wall, but also the rate of heat transfer as well. Okay, because if you're getting a lot of slip at a wall, that means you're getting a lot of dissipation. And the question is, right, what's the temperature of the material at the wall as a result of it being sheared? Because it will do that work against itself. And the polycarbonate, of course, is actually a very good insulator. So that means all the heat stays in the material. Whereas the stainless steel and the carbonate, or the stainless steel and the carbide, are much better conductors, so they will take the heat away. And you don't need a big change in temperature to change the rheology of something like soap. I might have answered that question already. Okay, so then let's get on to the last bit. We've done all these measurements. Okay, how do we then simulate or calculate what will go on in a forming operation? So the first thing we would do is, right, let's say we use computational fluid mechanics. So we set up the we set up the Navier-Stokes equations and we solve them. We have to come up with our, we have to come up with our constitutive relationship, and a very common one in the world of viscoplastic fluids is a Herschel-Bagley fluid. Okay, so it's got a bifurcation below some criterion for yield stress or critical stress. Your strain rate is 0. Above that, and this is the deviatoric shear stress, you have a relationship which gives you the relationship between the stress and the local strain rate. And usually this is done in a Eulerian way, and you capture the strain rate. So here we have two of the results that Matt Bryan did in his thesis. Okay, in terms of a square entry die, the dashed line is the plane of symmetry, the axis of symmetry. So this is a cylinder for different Bingham numbers. Same fluid, different Bingham numbers. And the Bingham number is a relationship between the yield stress and the viscous stress. So a Bingham number of 1 says your viscous stress and yield stresses are comparable. Okay, and that says that material, these are streamlines, and it's telling you that the slow regions are just in this little corner. Okay, for a slip coefficient of 10 to the 0. Okay, so this is a Navier slip coefficient. These things all change if you change the value of beta. And the solid line here is the shape that the material, in this case a microcrystalline cellulose material took. It sort of basically hangs out in the corner. Everything else is sheared. Everything else is sheared. It's all moving with max streamlines. If you go to a Bingham number of 10, which means it's 10 times more stiff in terms of yield stress, you can see it makes a big difference in terms of the size of this, let's call it a static zone in the corner. But also we see that the region where it starts to shear starts to come down and get quite close to the die entry. So up here, everything is shearing. Here, these are effectively a static region in the barrel. And this is information you need if you're designing a die, because you need to make sure that the barrel is the right shape so you don't get these static zones in the wrong places. Now, these lines are streamlines. The material is still notionally moving. Remember, we're saying that's what you do with a fluid mechanics model. These are all mapping strain rates. Whereas in reality, the stuff in the corner isn't moving. So this is an approximation. Now, there are other ways of doing this, particularly using augmented Lagrangian Eulerian methods in viscoplastic fluids. And they work quite well for 1D and 2D systems. But for 3D systems, they're a real challenge. And for 3D systems with pressure-dependent slip, well, Matt didn't get it to work. So we move on to the other method, or one of the other methods, okay, which is to use solid mechanics approaches. And this is what Harry Ayton, who just finished his PhD, was working on. And he was getting these pressure-dependent wall set functions to go along there. And there you might work with a thing such as a Cocker-Simons material, which relates the local plastic strain rate. That's what E dot super bar sub PL means. And there's your von Mises stress. So you need to work out your von Mises stress, the deviatoric stress in the material. This is your sigma naught is your characteristic yield stress, and DC and ZC are the parameters to describe a Cocker-Simons material. Now you can actually rearrange that equation so it looks like a Herschel-Buckley fluid. But the key thing is it's working in terms of plastic strain rather than a simple strain. And you do this in a Lagrangian method and you calculate the strains. But what you have to do is keep updating your strains, and this gives rise to these adaptive remeshing codes. So you find that the mesh evolves over time depending whether you have a smooth wall or you have a rough wall. Okay, and the world of adaptive remeshing has come on an awful lot since Dan Horban did his PhD back in 1999. Okay, and this is all fully programmed in a whole series of codes, and there's some really good codes that can do this, such as Forge 3D and things like that from groups in France and other places. Now, we're not a numerics group, so we're not the people to come and ask about how you would do this. There are some really, really powerful codes out there. But the last approach I'm going to talk about is something we have done something which is a bit special, which is, it's about streamlines. Sorry, just to go back to this. So here's the streamlines you calculate from one of these methods, and this is your von Mises stress. And you can see here in this case, all the material in this conical entry die is now in a state of shear. Okay, this is not a fully rough wall, so in fact, this angle is such that you don't get material captured in the corners, which is good, because if material stays in the corners, usually it does things because it's been hanging around for a while. So getting back then to the last approach, which is actually getting back to the nature of a paste, which is treating it as a soil. And the reason for this is that we've spent quite a lot of time working on when pastes don't behave very well. And in order to do that, we have to understand how the liquid phase and the solid phase moves relative to each other. And just to remind you, or to inform you, if you've never done any soil mechanics, what you do in soil mechanics is you say that your total stress, sigma, you split this up into a solid stress, which is the stress acting on the solids, which is a three-dimensional deviatoric stress, and the pore pressure, which is the pressure taken by the liquid, and it's a simple pressure. And what you have to do is link the two together. To cut a long story short, you can do extrusion, ram extrusion for soils. And this is one of the results from Mill and Patel's work a while ago. Here you have the total extrusion pressure for a given value of the velocity over the barrel diameter. So that's what scales this to the shear rate. And what you have in red here is the solids pressure. Okay, so effectively this is the stress acting on the solids. And I think the thing you can see is there's a big difference between this value and this value. And that tells you that most of the stress is being taken up by the liquid, because this is all that the solid is carrying. And at this lower speed, you can see that there's that's the total amount, that's the solids amount. And so that's the total amount of stress being taken up by the liquid. So the liquid is basically being squeezed. And that will cause it to want to move. And if it moves, it means your material is going to change composition while you're extruding it. And that's not good. So here you have the result of this. So here we have, trying to find my cursor, yep. Oh, there it is. Hello. There we go. Right. So this is the ram displacement in an extrusion, and this is the total pressure that we're measuring. If we go at 5.8 millimeters per second, we can see that it raises up the pressure. Then over time, the pressure gets bigger and bigger and bigger. And if we kept on going, you get bigger and bigger and bigger still. Whereas if we go 10 times faster at 58 millimeters per second, it reaches an extrusion pressure and then carries on like normal. And this is called liquid phase migration. This is the fact that the liquid is moving relative to the solids. And effectively, you're building up a region of compressed solids in the barrel of the extruder. So one of the things you can do with a soil mechanics code is replicate this, and also you can map the voids ratio. So this is effectively the composition of the paste. And what you can see in these cases here with a square entry die is in this corner, if I get this to work. Hello. Oh, we've got a little bit of lag. But anyway, in the corners, you can see there's regions which are quite dark or darker. And that means that they are building up solids. There's less liquid. And what happens here is we extrude a paste which has got liquid in it. We can actually, by extending it, this gives rise to the phenomenon of dilation, which means effectively the extension of the material sucks the liquid out. So it actually sucks it into itself and makes the liquid move. And you can see on the plot there, with these conical entry dies, you get much less change. So this is what we'll be doing in terms of designing a die, is trying to figure out what shapes will minimize the amount of low voids content. And so it means we can use it continuously rather than having to stop and clean it out. So that's a rather specialized niche thing, and it's really at the limit of finding out when certain geometries would not work well for extrusion. So come to the end of the talk. Closing remarks. Hopefully you've realized that actually pastes are all around us. They're in widespread use. They're just not often called pastes. In terms of engineering, paste engineering or practice leads paste science. So the book by Benbour and Bridgewater was published in 1993. There isn't really a paste science book yet, and I'll just explain some of the reasons for that. One is that they're complicated systems. They're multi-phase because we have solids and liquids, and those liquids can, of course, be complicated in their own right. They're multi-scale, not only associated with the geometry of the system, but also the particles. And of course, a lot of people mix particles in making paste. They just don't use the same size. And the complexities come from the fact we can have different sizes of particles, different types of particles in that. The rheology of the binder isn't necessarily Newtonian, and we've got these wall interactions. So in many ways, it's a good engineering topic because we can't really say one simple theory will answer everything. What we have to do is develop ways of treating the materials we're dealing with and identifying what are the most appropriate models for describing how they behave. So in closing, I just need to say thank you to a few people, okay? The people at the bottom who have supported us through this, and especially Sarah TSED, I've said for the last few years. And this is Harry, who's just graduated. And this is one of the reasons we like working with Sarah TSED, because they work in this part of Austria. So every so often we have to go to this part of Austria for a visit with the sponsors. Okay, this is Matt, whose work I've showed Sarah, and Michael, are Harry's co-supervisor. Sarah and I have worked a lot on liquid phase migration. This is John Bridgewater, who was the, as I said, the person who gave me the job. Millen and Stuart Blackburn are the people who worked on the soil modelling. Mike Johns and Eloise worked on the MRI group. And this is Roland and Brendan and Harold, who are the first people who work with Sarah TSED. So the last thing to say, or rather the last thing to say, is this. Now, I'm not very good in Portuguese. Obrigado por ter vindo. Alguma pergunta?
You did it so well. I wonder whether Silvana helped you with this.
No, this is Rubens, okay? Rubens Rosario Fernandez, who's just finished to move to Illinois, my local contact, okay?
Oh, yeah. That's great. Yeah, thank you very much for putting together such a lovely presentation. It was really interesting. There are a few questions here.
Okay.
I just got them from our collaborators in the YouTube. So the very first one goes like this. What strategies can be used when MRI is not a viable option?
Well, we start with what is viable. What sort of temperatures and pressures do you have to work with? So we typically have used RAM extrusion because it's pretty robust and relatively reliable. It is tiresome in that you have to get issues to make sure that the material loads properly. And again, it's all to do with the sizes of the yield stresses that you're working with. Because if you're talking about yield stresses of the order of kilopascals and bigger, your standard systems won't work. And normally you would miniaturize the system in order to get access to that sort of information. But the pastes have a dimensional limit in the number of particles or the size of the particles. So as you get smaller and smaller, you then would lose the fact you're actually measuring the bulk. So if your particles are 100 microns, you need to have gaps of several millimeters in order to get consistent sort of systems. So that's why we have tended to use RAM extrusion or capillary rheometry as our benchmark. If we can get away with something else, we would.
I see. There's another question here which calls for slide number 20, and it goes like this. Instead of two diameter reductions, do you think a constant reduction of diameter in a conical shape would result in a lower shear stress on the walls? So that's the question.
Yeah, I mean, you could do this with a conical diameter. Obviously, it can't be too sharp because then you're looking at an extensional system. So one of the things we have here is that we're quite happy with it being in a 1D sort of system. And people have used conical systems as well because then you're capturing you're capturing an evolution of velocity as well. So as long as the system isn't very pressure dependent, because the plot I showed you here showed a nice linear gradient. If the system is pressure dependent, well, then this is no longer straight. because the first point here is at a higher pressure than the point below, which means you then tend to get curvy lines, if I can put it that way. And that's one of the reasons why we kept it as a cylinder, because effectively we are getting our first dependency on pressure, and we are always looking at the same velocity. So in principle, you could do it with conical systems. You have to then be able to decouple the absolute pressure effect from the local velocity when you're doing that.
Yeah. Ian, if you go back to slide 20, please. One of the things that came to my mind when I was looking at this device is how did you guys come up with the distance in between the pressure transducer? Do you have to play a little bit until you get it right? Or, I mean, how did you come up with that spacing?
Well,
I mean, is there, I mean, at the end of the day, the question is, I'm wondering whether if you change the material that you're trying to measure the stress, for instance, that distance would play a role, or it will work for any material?
That's a good question, Sabi, and I don't know the ultimate answer. One of the reasons is it's a couple of die diameters. So just on a geometrical relationship, let us have it a couple of die diameters apart. Okay, so if there's anything related to length scales in that flow, we would do that. The other point is, of course, how close can you get them to be in terms of machining the things? Because these pressure transducers they're not that small. Okay, and so you do have a confinement issue. This is one of the reasons why in the latest version they are located at different positions around the cylinder, so they don't interfere with each other.
Okay. Yeah.
But the other thing you could do here, of course, is you could change the nature of the wall. You can put a liner in there, and then you'd be looking at, well, as long as you have to match the liner up with the pressure transducer, but then you can look at different materials as well.
Okay. There's one question here. It says, you've mentioned the problems some materials can have regarding heat dissipation due to the shear stress. So what about the paste materials? How can they be characterized in terms of heat conductivity? So that's one question. And then the second one, can the temperature during extrusion be high enough to affect the quality of the final product?
Okay, I'll start with the first one. The thermal conductivity of the material, well, obviously it depends on the nature of your particles. Okay, tungsten carbide, it's pretty dense, so it's a very high thermal conductivity. So whereas more food materials tend to be around that of water or smaller. Okay, so that's very much, it's related to the nature of the material, but also whether or not there's any orientation of the particles as a result of the flow. Because you can imagine with, let's call them plate or disc-like materials, they can actually orientate in shear, and that means you end up with a thermal conductivity in one direction being different to that in another. Okay, because you're lining everything up. Now, can the dissipation give rise to changes in the material? The answer is yes. Okay, two classic examples. The first one is ice cream. When you're pumping ice cream down a pipe, the dissipation causes friction at the wall, which locally melts the ice cream at the wall, which means that the ice cream flows happily down the pipe without melting. Okay, so actually in this case, viscous dissipation is quite good. If you try and take the heat away, that means that it will create more dissipation in other parts. So we had a paper on that a while ago. Sadly, we never got to get any ice cream. We were just given Another one is we did some work with starch-based paste for making, let's call them food snacks. And there, because the binder was water, whenever it got enough dissipation, you actually ruptured and denatured the starch. And actually, this comes back to the Horobin work. If I go back to this plot, Yep. So you imagine this rough case where you had very high strain rates. That meant you had high local dissipation. And this actually gave rise to the generation of a film of ruptured starch around the extrudate. Effectively, it was creating its own sausage skin. Okay, you actually had the material, you're adding it on the perimeter there, it was creating a film which then held the material together. And the product was then cooked, which meant you couldn't tell that this had happened in the extruder. But whenever we went and sectioned the extrudates here, you could actually see this lovely material just holding it all together. So yes, if the rate of dissipation is high enough, and particularly with wax-based binders, which is what we were working with Sarah a while ago for the tungsten carbide systems, they're very temperature sensitive. So we had to do quite a lot of work in trying to control or characterize the temperatures in that work.
I see. We have probably one final question, which is there any wall coating that could be used to lower the shear stress on the walls?
Wall coatings, there probably are. The thing is, what you're trying to do is design a wall coating that repels particles. And the particles, of course, are forced against the wall because of geometric relationships. So it's not the same as a polymer affecting friction in a flow. Well, these systems are very dense, so the particles will be pushed against the wall. And there, the issue is, can you get something that promotes sliding of the particle along the wall? And also that means that the coating is hard enough not to be abraded by the particles. And with the tungsten carbide system, that's one of the issues, because effectively you are extruding abrasives. And that's why we have tungsten carbide tooling, because that's the only thing you can extrude tungsten carbide paste through. Well, and still have an extruder at the end of it. So yes, there are possible, and it really depends on the chemistry and the strength of the coating versus the particles. There's a lot of work to be done here in terms of relative hardness of particles against material and things like that.
I think we are starting to run a little bit late. I have more questions here. I can probably email you them, and then if you answer them, I'll pass them over. But it was really nice to have you on board with us and share some of the research that you guys have been doing. I can see that you have a very nice sponsor. I mean, you don't go on a business trip. At the end of the day, you go on a holiday trip, isn't it? Yeah, I'll keep quiet.
Fabio, I think that people there around you need to know just how flat this part of the world is, right? So that's why it's so nice to go to that part of Austria. Yes, it is a very different part of the world.
Yeah, it's very peculiar. Yeah. Okay, with that, probably we will end up for today. And again, Ian, thank you very much